Okay, so here we're going to take a look at simplifying expressions and proving some tautologies. Right? One thing to keep in mind is the substitution laws. What makes it an algebra? All right. All right. So here, for example, here let's take a look. Give me 1 second here. Now, if we look at here in this part of our textbook here, this figure 1.2, we have all the laws, and it looks like these laws just apply to propositional statements P and Q. But really, the nice thing about this algebra here is that we can they apply to compound propositions as well, right? So compound meaning that they involve more than one proposition, right? So and using these substitution laws makes these these laws are much more powerful than at first it seems, right? So let's take, for example, here we have the first substitution law, right? So this states that if Q is a compound proposition, and P is a propositional variable, substituting Q, you can substitute Q for every occurrence of P, right? You can sub Q for P in a tautology. Right, and it will still be true. It gives another tautology. Right, and our second substitution law, right, if P is logically equivalent to Q, then you can just replace any occurrence of P inside of a larger expression with Q, and it preserves the overall equivalence. All right. Now, with these substitution laws, that allows me to do the following, right? So our first example here, right? I want to show that P or P implies Q is logically equivalent to P and Q. All right, so again, here let's start out with this P or Q. And from earlier in the semester, I know this implication is equivalent to not P or Q. All right, that's the definition of P implies Q. Okay. All right. Now I'm going to use the distributive law here. All right. So we have here the distributive law states I can have P and not P, or P and Q. Okay. Okay. All right. And now here what we have is the law of contradiction here. So this is false always, and P or Q, right? So here, distributive law of contradiction. And then this is P or Q, and that's the identity law. Okay. All right. So the final result, P and Q, right, is a much simpler, and we know it's equivalent because of all of the work that we've done here. So it's much easier to verify instead of verifying this with a complicated truth table. We can just simply look at a much simpler version, P and Q, to be true. Okay, so that's kind of the advantage here of these laws. You can use them to simplify expressions to have something that hopefully much simpler. All right, so let's look at another example where we want to prove a tautology. So a tautology, again, is something that is always true. All right, so I want to prove that P or Q and not P implies Q. It's a tautology. All right, so the goal here is that through our laws here, I want to reach the conclusion of T, true for all values of P or Q. Okay? All right. So we'll start here with we have an implication. So let's just use the definition of an implication. So that means that we have not here the hypothesis, right? So not P or Q. And not P or Q. All right, so that's just the definition of our implication. All right, and then from here, I'm going to use De Morgan's law. So De Morgan's states here that we want to negate here P or Q, and then this goes from an and to a or, and negate not P. And again, or Q. All right, so this one is De Morgan's. All right, and now let's use here, we have a double negation here. So this, oops. All right, so the double negation here, and I'll give myself some more room here. Not P or Q, or P, and then or Q. Okay, and now we are going to use the associative law here. Okay. All right, so our associative law here, we can use to rewrite this as P or Q P or okay, so we can associate these terms any way we want, and if we associate them this way here, okay, and here this one is double negation. All right. Okay, so we can use the associative here, and again, notice here now this is the law of the excluded middle. Even though, again, right, recall that substitution law where it doesn't necessarily have to be a proposition. It could be a compound statement, right? We have P or Q here. So the negation of P or Q and, excuse me, not and, or P or Q, that means this is always going to be true. So we arrive at our desired conclusion. We have a tautology, which means the above statement is always true. Okay. All right. And then this last jump here is the excluded middle. All right. Okay. So here are the techniques. Apply one law per step. Cite it and just keep going, right? One step at a time. Laws go either direction, and then factor or distribute as needed as you try to prove these statements or tautologies. Okay.